Good morning. Just looking around the room and realising there's about at least 4 people in here who know more about this than I do. So this is going to be interesting. Just going to start talking today and find my notes. About using Go with a tool called Antler. So not actually anything to do with these animals which are apparently extinct now, which were horned gophers. Like all great engineering stories, it starts with a fairly simple problem. Just want you to build an API that allows users to retrieve their data. Of course, there's a few additional problems in here because what we actually really want is, we kind of think about it, just build a simple REST service sitting on top of a SQL database, job done, be done in a few weeks probably. Turns out we actually have a REST API to do this. Doesn't really work. Our data model is quite complex, quite interconnected, so it's not going to really play ball. Okay, our users want SQL. That's fine. We'll expose an endpoint which allows users to use SQL. Restrict the write access. Again, job done. We'll move on. Apparently, that's a little bit cumbersome. Don't really want to do that either. Okay, we'll look at some other tools that are around. Let's write a DSL. Let's figure that out. Some security issues with that. So before we had a fairly big look around, we decided actually that what we really wanted is a bit of a graph database. And we looked around and we quite liked Neo4j and its Cypher language. Of course, the trouble with again, providing direct access to your database, generally not a great idea. But also at the time, Neo4j was the only database that spoke Cypher. So we're a bit worried about things like vendor lock-in. We obviously still need to figure out how to control the write access. What if we ever actually wanted to extend the language? What happens actually if Neo4j, Cypher is fairly new? What if they actually go off a completely different direction than what we want to be able to provide our users? So what we want to be able to do is just extract the meaning out of here. And obviously being developers, first thing we start thinking about is regex. Can we write a regex on top of all this, pull out all the meaning and move on? Anyone who spent any time with regex is going to say, nah, that's going to be pretty horrible pretty quickly. The complexity, the maintainability, the extensibility, how can we ensure that it's actually matching stuff that we want? How can we ensure it's not matching stuff we don't want? All the usual sort of stuff. So kind of went back to basics and had to think about it. And we're like, well, this is actually a fairly simple, well-known problem. We've got a string. Computers don't really like strings, but we've got a string that humans like, and we need to be able to break out that string and figure out the meaning. Forgot about another little Ryan there. And don't have emojis on this. Great. Computers essentially, programming language, love data structure, so we need a way to kind of take a string and turn it into a data structure. And again, this turns out to be a fairly solved problem. This is all we want here. We need a lexer, some tokens, and a parser, and hey presto, we get a parse tree, or the official name, an AST tree. So that's just what we need to do. Tokens, lexers, parsers, parse tree. We're all good with that, right? Just move on. So let's quick bit of back to school, figuring out what these things are. So we need something which is a grammar file. So these strings need to comply to some sort of grammar. So in this case, we kind of have a bit of a look here. Got a match clause, which is pretty much defining what a match thing is. There's some sort of relationship between actors and acted in movies. And there's some sort of return statement saying we want to return some bits and pieces. So again, at top level, makes some sort of sense, but how do we actually do this? Well, first off, we need to define what the words are. So if we take a look down this kind of simple example here, we've got a few different things. We need a var name, or SP. We need an end of file statement. Need some sort of assignment statement. Need some way to figure out what the num-vals are. All the general things. Break up all the actual meaning in terms of the tokens. That's great. Okay, we can define these things. Next step up is our lexer, which essentially just takes all those strings, iterates over takes all those tokens, iterates over the string to be able to then create a token stream, just simply walking over the string and returning the tokens that it finds in there. And then all we need to do is define what the parsers are. And this is the fun bit. So once we've got our token stream, we actually need some way to figure out what's the meaning behind this thing. We need to be able to then say that actually SP equals 100. How can we tell if SP doesn't equal some other nonsense? So essentially this is where the work is. Every single token needs its own parser, and we need to then figure out all the different ways that parser can be split up, essentially breaking them down into nodes, statements, and expressions. So there we go, all done, job done, we can move on.
So that is basically how we've defined our grammar. How are we actually going to use that? We're going to use something called ANTLR, and this is where you see the change in the tide here. So what ANTLR is, it isn't a language, it isn't necessarily a grammar, it's a tool. It's basically a Unix tool, the same way as grep, set, all those things. What it is, it stands for another tool for language recognition. So what we do is we supply it a grammar, we run ANTLR, and it basically will provide us all of the things that Roger's just described, the tokens, the lexers, the parsers. How does it do this? Or sorry, what does it do this in? It's essentially a code generator. So whenever you give it the grammar, it will generate all of those things in the language of your choice. So basically it has these targets. For those at the back that may not see the bottom, there's C++, Java, Go, Python, C#, Swift, and JavaScript. So you can use your grammar in the browser, you can use it in the back end, you can use it more or less anywhere. How do we run that? Really simple. As I said, just a command line thing. So the most recent version is called ANTLR 4. The target, the language is Go, and then you basically just pass in the grammar file, which then generates all of these files on the left-hand side. ANTLR itself is written in Java, but you're not committed to it. As I said, it has all of those other targets. You don't have to worry about what ANTLR is written in. It's just they're mostly for portability, so obviously you can run it on Windows, Mac, Linux, all of those things. The nice thing about it is 90% of these files that it generates on the left-hand side, you don't have to care about. So, sorry, I'm going to go wandering here just because it makes my life easier. So this G4 file is the actual grammar file, which we'll have a look at in a minute. All of these are machine generated. Whenever you run ANTLR, and you run git to basically generate the new grammar or your new files, those are going to change because they're all machine generated. They're a bunch of integers. If you look at them, it is just a descent into madness. The rest of these are all generally just base things that you can then build on top of, and we're going to have a look at those in a second. The one that you'll not generally see, because I've thrown off the argument at the end, because it's probably over here somewhere, is this query language underscore visitor. So there's two things that ANTLR will allow you to do. This isn't going to work, but we'll give it a go. It allows you to generate a listener and a visitor, and basically that's a way of iterating through that parse tree that Roger was talking about. The one we care about is the visitor, because we want to do very specific things with it. The listener is basically, it starts at the top and it basically bounces its way through, but I'll go into that in a wee bit. So we've generated our files. We'll have a look at the grammar. So this match clause here is what Roger showed you earlier. And basically what this says is, using this match keyword, and then there's going to be some white space, then a node, then maybe some more white space, a relationship with maybe some white space, and then another node. And basically what we're saying here is there could be many of these, and the question mark says it could be optional, more white space, and then return value, potentially many return values. The likes of the brackets, plus signs, question marks, those seem familiar if you're using regular expressions. And to be honest, they're not actually that different. But what ANTLR gives us ahead of regular expressions is it gives us a much more formal way, rather than using back references, trying to name things, all of that sort of stuff. So basically, what this match clause will represent is this query here. So we've got our match, which ties to the match, a piece of white space. Then the node is this piece here. The relationship is this piece, then another node, and then our return statement. But we'll dig into that. So if we look at our actual node, as you can see, open round brackets, close round brackets, and then we've got an alias identity, which will be the A:\actor. and then a filter, which will be the curly brackets and everything inside, and then potentially multiple versions of the filter. And here we have our alias identity, where we've defined an alias and a node name. So we have the A from the top here as the alias, and then the actor as the node name. And then this bit here, the pipe, basically says, for this alias identity, we can actually have multiple things that this could be. So it could be an alias colon node name, or it could just be colon node name. And then filter is basically field, colon, and then a field value. And then getting really into the nitty gritty, looking at that field value we had before, what this is, this looks terrible, it's basically a double quote with potentially some white space. We're trying to be nice to our users. And then any text, some white space, and then maybe more text. So basically what that allows us is, if we didn't have that bracket, it would basically be one single word enclosed in quotation marks. Because we have the white space and more text, we can have multiple words with spaces in between. What is any text? Any text is down here, which is basically our Unicode symbol classes, which we've defined as any character. Any lowercase a to z, uppercase a to z, 0 to 9, or an underscore, or there's a space in here as well. So that's it. Not terribly different to regular expressions, slightly more verbose, but much, much easier to work with. Why is it easier to work with? Let's say that I decided my field value can't have any numbers in it. I just take it out of this, I just take this 0 to 9 out, regenerate my grammar file, and that's it, it works. As opposed to hacking back, trying to remember what is this, if I take this out, what will happen, doing all my tests, have I introduced new bugs, all of those sorts of things. So that's the grammar file. This is what we do with it. So who has used Go in the past? Okay, excellent. Who's used Java? Okay, sorry, bias. So it's not complete. If you know Java, this should be reasonably similar. It's kind of C-like more than anything. But so we have a function called parse. We're passing in a query string, which will be the match, blah, blah, blah. The weirdness that you may think is there's two return arguments here. So we're passing back a query context and an error. So a query context is one of those things that that Antler has generated. It has generated a Go struct for that particular thing. We didn't do that. Antler did that all by itself. So what do? We create a thing, we create an input, and we just create a new input stream from the query. That's the stream that Roger was talking about. Then we create a lexer, which is going to tokenize the whole thing. We then create the token stream and then pass that into the parser. And then what the parser does is it's going to actually build that tree for us. This bit here basically just adds error listeners. So what this really does is it's a lot of programming to interfaces, which the Go and Java people will be familiar with. So it basically says, rather than returning an error, you just need to check for it. So what I'm doing here is I'm getting my AST, I'm asking for my query back, and this is just me casting it to this particular context. If there was an error, return that, otherwise return the actual query AST. So we've got that. Now what? So this is what we're actually going to do. So this language.parse is just running that function that I showed you there, and it's passing in this as a string. If the error is nil, then it can't parse it, otherwise just print it out. So what I've done here is I've ran this file, I've passed in this and got this, I've passed in, this statement and got this back out. Well done, you've just copied the exact same statement. Yes, granted, not terribly impressive. What is slightly more impressive is the subtle difference between that statement at the top. If you look, it says match name buried. There's no quotation marks around that, so this isn't a valid statement. If I run this, I'm going to get could not parse error, syntax error at line 1, column 22, extraneous error port buried. It's basically telling me I was expecting a quotation mark, some white space, or a number. We get all of that for free. So basically, rather than me trying to, right, where my regular expression, did this fail, all of these sorts of things, I get all this for free. If I change my grammar, update the grammar, I still get all of my statements just parsed for me. So that's pretty cool. So at this stage we can go home, right? Then the project manager steps in. That graph database, yeah, it's pretty sweet, but my customers, they still want some SQL, but we still want to use the same query. Every developer goes, I hate you so much right now. So we have our match, our query that we had. What we need to do now is convert this into SQL. And this is where we start getting into the visitor pattern that we were talking about. So this is the AST tree that we were talking about. So literally what it does is we had the query, we had the match clause, and then it's broken it into all of the different components and then subdivided those down. And what we're going to do is basically just step through these, look for the interesting parts, and then extract those out. And again, we get all of this through Antler rather than trying to do it ourselves. For those that don't know the visitor pattern, I'm going to be honest. I am an engineer and not a computer scientist. So my degree is actually electrical engineering. I have very little clue what this actually does. What I do know that it does is it allows me to actually go through each of those nodes and pull out what I want. And this is the difference between the visitor and the listener that I was talking about earlier. What the listener will do is whenever it's parsing, it will literally listen. It's more event driven. It'll basically listen for, I'm in this thing, what do you want me to do with it? Whereas here I'm going to go, okay, I want a node, and then I want the alias identity, and then I want the alias, and then start pulling those out, sort of fine picking. If you're old enough like me, and before the days of jQuery and things, back whenever XML was popular, it's the difference between using DOM and SEX, essentially. Where basically instead of doing streaming like SEX, which is the listener pattern, visitor is more DOM. It's basically saying, I want this specific node. So what I'm going to do is I'm going to try and pull up Goland here. So this isn't terribly visible, but I'll do what I can. So let's start at the start. Or wait for the beach ball to go away, one of the two. To talk amongst yourselves while, oh, there we go. Right, so again, this is very small, but bear with me. So again, for those that haven't done Go, it's kind of C-like, in as much as there's a lot of what would be C structs, but they're familiar enough to Java classes that they're recognizable. They're not classes, they're structs, apparently. I'm not entirely sure what the difference is. Anyway, so what I've done is I've created an identity struct called an identity, which has a name, an alias, a field, and a filter. And what we're going to use those for are those particular nodes where we had that a:\actor. So that is the alias and the name. And then the filter is those curly brackets where we had the field name and the value that we're going to look for. And what we're going to do is we're going to embed that into a relationship struct and also a table struct. The reason we do that is the structures are the same. Basically, it's the same structure in the Antler that we're using, but we basically want to split those out because we want to work with relationships differently to tables. Why do we want to do that? Because this is our table. And basically what we have are a bunch of functions that we've added on to that struct, which we'll use to generate our SQL. And we'll get to that in a second. And then we have a query, which right now is just basically a bunch of tables because I thought I wouldn't embed all the relationship stuff because who wants to complicate that? And then finally, this is the SQL visitor, which is the bit that we actually care about. So what I've done here is, you can't really see this, but this struct is SQL query visitor, and then I've embedded a type called the base query language visitor. This is the one that Antler has generated for us. And basically what this means is whenever I want to call through this, if I call a method, let's say I want to almost implement that listener pattern. If I call a method that I haven't actually implemented, it'll call the base one. And all the base one does is just continues on down the tree. It doesn't do anything. I'm basically overriding the functions that I actually care about. So, a lot of this is very repetitive. We have visit query, which is basically where we start dealing with our query. And again, because Go is typed, you end up casting a lot, which is what most of this text is. So what I'm going to do is I've passed in a query context, and again, that's the one at the top. And I'm basically iterating through all of its children, which will basically go down a level and say, give me all of those. The one I care about is a match clause. So I've got a switch here, because I'm doing a switch on the type. It's a match clause, and then I basically jump down into this function. Visit the match clause, look at its children. Okay, I want to look at the nodes, and I want to look at the return values. So the nodes first, I'm going to visit the node. And this is where we start doing stuff. So, I've lost my place. There we go. So go through the nodes, get the children. So what I'm looking for are the alias identities and the filter context. So basically what I'm going to do is I'm getting the alias identity, pulling that out into its struct at the top, which is one of those structs that we looked at the very, very start. And we'll look at how, oh, actually we can see it here. So this is the visit alias identity. I'm assigning the alias and I'm assigning the name by going through its children, passing that back up, and then adding the filters in. So those filters are basically our search parameters. Basically, all of that's the same throughout. There's no point in boring you going through everything. And then we basically have our main function here. So run the code, pull in the first argument, which should be our query. We're going to parse our string. If it's not valid, we're going to say we can't parse it and why. Basically saying your string, your query didn't work. Give me something that works. Then print the actual, string, our query again. Then we're going to pass it into this new query, which is just a function here. So basically, create an SQL visitor, pass in the tree that we've generated into visit query, and then pass me that query struct back. And then finally, we're going to run query.sql, which we haven't looked at. So query.sql is just a method on the query struct. And what this is going to do is it's going to actually generate our SQL for us. So using a string builder, I'm going to add a select. I'm going to build up the fields that I'm looking for from the tables and my return statements from before. I'm going to do my from. All those tables that I've pulled out, I'm going to add those into the from statement. And then the return clause, the filters, the where clause. Sorry, it's been a while since I've SQL'd. And then pass back that string. So what is kind of interesting is these fields that return select, and this is why we made a separate tables versus relationship. So return select is let's look at the return from. So that's basically where I am going to explicitly say the table name as the alias. And the relationships, we would do that slightly differently because those are our inner joins. So our return from with a relationship is going to be slightly different. So what we then get back is, given that, pass in the query and get our actual SQL statement back. I was really hoping for a round of applause there, but never were. Is this a good idea? Well, sort of. The SQL demo isn't something we actually did, although we did talk about it for better or for worse. Actually implementing your grammar is potentially a good idea, depending on what your use cases is. One of the use cases that we'd looked at in Flexera is we have our query. Rather than using regular expressions, we've actually got our node names, we've got all the fields and everything that people are searching for. Let's pull all of that information out, dump it out, so we can actually do some analysis on it to see what our customers are actually looking for. We could also use it for applying business logic. So our customers have paid for access to these fields. We're only going to give them access to these fields. So if they try to access something else, then we can basically block that off at a grammar level. In our customer field, have you paid for this visitor? Applying programming logic, basically this allows us to do things like formatting the statement for the database. So for for talk's sake, this isn't true, but if Cypher was case insensitive on Windows, but case sensitive in Linux, we could basically format things in the actual query statement for Linux itself. Then you get fun things like applying complexity limits. So we can actually pass in a query. If we assign a value for each, or if we assign a cost for each thing, so let's say a node is 0.1 and a relationship is 0.2. If we accumulate that up and it's over a threshold, we can basically say, sorry, you can't run that query. It's too expensive. So go speak to your account manager and we can maybe take that off for you. And then other stuff, smarter people than me can think of. So our use case was really specific. There are other use cases, so in your own business, there's probably things that you could do. If you're working on a game, you could have some form of grammar parser for user input if it's a text adventure to basically pull things out, start doing things like that. What are, your doing words, what are your nouns, your objects, things like that. Even in, if you're in security, going through logs, assign ways to parse the grammar in your logs to actually extract things out. There's a million different things. It just takes a bit of thought, usually drunken, to try and come up with them. Has anybody any questions? Thanks for coming, by the way. Just a statement from me before the questions. I appreciate this is probably one of the drier talks, so thank you for not having anything better to do. Sorry, go ahead.
Sort of how self-contained is the generated code? Do you end up having to pull in many or any transitive dependencies?
No. Literally, it is pure whatever your language is. It literally generates. For the Go stuff, it pulls in an Antler library, but that's the height of it, and all that does is basically give you the base types that it uses to reference. It was only 10 or 15K, so that's pretty small.
Had you considered growing your own parser?
We did get that drunk one night, yes.
Yeah, early on.
Changed the project time to 2 years.
Yeah. Yeah, Antler allowed us to do it really, really fast. Anybody, any other questions?
Do you get the error handling by default? So if you, or do you have to code in if you find this, return this error?
I can actually, so what we had there, if I can show you that. I know you're going to shout at me, Glenn, bear with me. Basically what you can do is, where'd it go? Yeah, so what I've done here is I've added an error listener. That's my specific error handler. So it basically allows me to format my error message.
Gotcha.
But all the error handling is done by Antler. Anybody else?
You must have run into some cases, or I imagine you would, where even relatively simple Cypher statements resulted in these massive SQL statements?
Well, we didn't actually we did, as I say, we didn't do SQL. What we actually did was Gremlin, which was an order of magnitude even worse. Yes, we ended up with some absolutely horrific things, which is basically why we ended up going back to Neo4j.
There's lots of side questions around what you're trying to do.
Yeah.
So there's definitely cases where you need to try and at least have like for like understanding of what's going on.
But the primary advantage that we got using our version of Cypher is it allowed us to pull out all the stuff we didn't want to support. So for example, if you try to push in an update or a write query to our grammar, it'll go, I have no idea what this is, so I literally can't do anything with it. Which basically means you don't have to start parsing through all of the statements going, should I pass this through or not? Cool, okay. Yeah.
Where these are options for I'm just wondering if you've looked at, or if you know if anyone has looked at possibly taking the output from Antler as a direct front end and something like LLVM, as opposed to going straight to the sort of endpoint where you can Swift or Go or C++, where it's it's giving those extra options of something like WebAssembly or.
Yeah, I have no idea. Engineer, not a computer scientist. I imagine yes, somebody has thought about it, somebody's looked at it, to be honest. It should probably be possible. Okay, so on Twitter, he is all of these people. I'm Tyndall. We'll be about for a while anyway. If you have any other questions, if you just hit us up on Twitter is probably the easiest way to get us. But otherwise, thanks for coming again.